Hey everybody and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy where we are learning networks together. And I have to start off this part of this series about EVPN-VXLAN. Here I go. That stands for Ethernet Virtual Private Network, Virtual Extensible Local Area Network. I always have to say that. It feels like it's a tradition now to start these parts in this series by saying what those acronyms are. But I have to start this part with a little bit of an apology. I haven't actually done a video for the last 2 weeks. That's simply because of life. There's no other reason other than that. I've been a little bit ill. I've also been on holiday and plus a bit bogged down, bit busy with work. Of course, life sometimes gets in the way of doing these YouTube channels. But I'm back. This is part 10. In this EVPN-VXLAN series. I'm not saying those acronyms again. You should know them by now. I definitely know them by now. And I'm really excited about this part because we are now getting into the configuration on the Juniper Junos devices on how to deploy EVPN-VXLAN. But I'm going to do so in 2 different topologies. In this part, in part 10, we're actually going to deploy EVPN-VXLAN in a spine only deployment. In the next part 11, we're going to do that in a spine leaf topology. Now, if you don't know what the difference is between a spine only and a spine leaf topology, highly recommend you circle back to part 9 to actually go through what's the difference between spine only, what are the benefits, what are the disadvantages, and how does that compare to a spine leaf topology. And even better, if you don't know what EVPN is, if you don't know what VXLAN is, I've done 8 other parts to this. Please check them out. Here's a link to the whole series. Highly recommend you start there before going further, because EVPN is a very powerful, very in-depth signaling protocol, and VXLAN is not so in-depth. It's pretty straightforward in what it does, but it's still just as important when it comes to the layer 2 adjacency over that routed or IP fabric network. So I'm not going to say any more as to what this part actually is, but there is a particular flow that we're going to do. First, because we're learning here, I'm actually just going to go through what is the plan in configuration, because we can't just go straight into EVPN, we can't just go straight into VXLAN. The network is pretty much not configured right now. You will see that in just a minute. So we need to have a plan of configuration where I'm going to define what we're going to do first, second, third, fourth, so on and so forth, and really build up to that configuration of EVPN and VXLAN before we do the validation. Of course, we need to validate it all at the end and make sure it's working. And when we've done all of that, when we've gone through the plan, we're then going to jump on the Junos and actually go through the configuration. Finally, after all these weeks, we're there. Yes, really excited. And so with that in mind, let's just jump straight on to the lab and actually go through what is the plan of attack. And so here we go. Let's go through this plan of configuration. Of course, we need to identify how we're going to actually go around configuring this network, but really understand first what are we actually going to configure in a step-by-step process. But first, let's actually look at the network. Obviously, there's still some hosts here, some virtual switches booting up. I'm actually using the Juniper new VEX virtual EX switches. So let's just hope, fingers crossed, that it's pretty good in terms of stability. I've honestly not tested this before on the VEX, so we'll see. But anyway, this is, as I've said, it is a spine only configuration. Now what that means is really from spine 1 here to spine 2 over here, we've got layer 3 running over this link here, so over the GIGI 000, GIGI 000 interface there. When we look at it from leaf 1, leaf 2 and leaf 3 up to the spine 1 and spine 2, everything is running layer 2. So as I said in the last video all those weeks ago, it's layer 2 everywhere. So what we're using to trunk VLAN 10 and VLAN 10 here, note that these 2 hosts are in the same VLAN over this network. We are of course using 802.1q, i.e. trunking. So what we've got is VLAN 10 going up to this spine 1 up here, and also across onto spine 2 here. And likewise for this host connected to leaf 3, we've got the VLAN 10 for that host being advertised or trunked up to spine 1 across this link, and across or up to spine 2 via that link there. So basically trunking pretty much everywhere. There's nothing on leaf 2, as you can see, because there's no real need to make things complicated at this point. Two hosts, 2 tenants in the same VLAN is more than enough to show the configuration in a spine only deployment. So the first plan of attack that we're going to go through is actually the IGP, the Interior Gateway Protocol. Now this is actually what's going to form the underlay routing protocol before we actually build on top of the overlay. Now if you've watched the previous videos, you'll know that the underlay is of course referring to a layer 3 network. We've got layer 2 from the leaves up to the spines, and we've got layer 3 between the spines. And obviously just going off what I just said, where IGP is underlay and underlay is layer 3. So that stands to reason we are deploying the underlay routing protocol, the IGP routing protocol, from spine 1 to spine 2 and back again. Now specifically for this underlay, what we're actually going to build is OSPF. So I quite like OSPF. It's standardized, it's open, it's been around a long time. The Dijkstra algorithm to use, the shortest path first algorithm, is very good in what it does. Obviously it's not as extensive as BGP for obvious reasons, but OSPF here is more than enough to build this peering from spine 1 to spine 2. It's more than enough. We don't need something like eBGP for the underlay in this particular case. But what is absolutely needed for this configuration is for both spine 1 and spine 2, we must advertise that loopback 0 interface into OSPF, and that is going to build onto the next part, point 2, and I'll come on to that in just a second. But specifically we're going to configure loopback 0.10 referring to that VLAN 10 that is within this access interface down to host 1 or down to host 2 over here. So we need to build OSPF in, say, area 0. I'm being a bit specific here, but just so you know the configuration, what we're going to do. So area 0, and we are going to advertise these loopback addresses into that IGP. So spine 2 learns spine 1's loopback address, and spine 1 learns spine 2's loopback address. And when we've done that, we can then build the overlay. Now, this is the second part. We've advertised those loopback addresses via the underlay. We've got the underlay built, hopefully. And at this point now, we are then going to configure eBGP external. And the second point is actually for the overlay itself. You probably just clicked on to where I was going with that. I kind of gave it away. But with the overlay, we're actually going to configure IBGP. So internal border gateway protocol. You could do eBGP as the underlay, but it's not needed, as I said. But we most certainly need IBGP for the overlay itself. And we are building the adjacency from spine 1 to spine 2 and spine 2 to spine 1 with these loopback addresses. That's why we need to advertise them via the underlay in the first place. And once we've got that built, we've got layer 3 as the underlay, and just here we're then going to start advertising all that network layer reachability information via IPGP. And EVPN is just building on top of this. So that's step 2. So first, just in quick recap, we're going to configure the underlay, OSPF. Second step, we're then going to configure IBGP, the group overlay between spine 1 and spine 2 and spine 2 and spine 1. The third step is we're actually going to start configuring the link aggregation groups, and I'm doing a slash here, or the Ethernet segment identifiers, or ESIs. And this is very important because with EVPN, we're dealing, one of the benefits of EVPN is it can deal with Ethernet segments, and obviously every Ethernet segment will have an identifier, hence ESI. But if we look at it from leaf 1's perspective, we've got this two groups of interfaces here going to spine 1 and spine 2. Now, Leaf 1 will see this as a link aggregation group. It is completely not aware that actually these are going to two different devices, because on spine 1 and on spine 2, we are configuring an Ethernet segment identifier, and there's parameters, there's attributes which have to match, such as the system identifier, and that kind of fools or tricks that receiving device, in this case Leaf 1, to believe in, I'm connected to the same upstream switch or router, whatever it may be, and I can now load balance all these packets to that same destination over multiple links. Great. So we need to configure the link aggregation group on the Leaf devices, but we also need to configure the Ethernet segment identifier on the spines as well. And the fourth step, we can't forget about this, is very important. These guys down here, the VLANs, we have to configure the VLANs on those Leaf devices. So I'm just going to do VLANs in bracket L here. So we need to configure the VLANs on those Leaf devices. But as a second step, we also, on the spine devices, need to configure the VNIs, the virtual network identifiers. If you don't know these acronyms, please refer to this link here, very important. But we're going to be configuring that VLAN to VNI mapping on the spine devices. So I'm just going to do in brackets S there to stand for spines. So we must configure the VLANs on the Leaf devices. They must also be trunked over those uplink interfaces from the leaves to the spine, so we can't forget about that. And then we're going to configure those virtual network identifiers on the spines as well. And the step 5 is we are going to configure the Anycast gateway. This is where we're actually going to have on the spine devices the Anycast or layer 3 gateway. So in this case, it's neither edge or core. It's really a collapsed core at the end of the day, with layer 2 south of those spine devices. So it's neither core or edge, it's just a gateway at this point. But we are going to configure that layer 3 gateway on those spine devices. And that's important because if this link here from Leaf 1 to spine 1 goes down, it's going to see that same layer 3 gateway over this interface here. So distributed, that's Anycast gateways. We've got the same virtual IP address, maybe the same virtual MAC address. It is recommended that you change the virtual MAC address by default. The Junos will configure a VRRP virtual MAC address. You can change it, it is recommended, but you don't have to. But that virtual IP address is that Anycast distributed IP address that it will be shared as such from spine 1 to spine 2. It's the same, and every leaf will see that same IP address on multiple spines in this case, or maybe even more spines. And then we're going to start actually going a little bit more into, or actually fully more into, the EVPN configuration. Now, EVPN is a huge protocol. The theory around it is absolutely ginormous. The studies that I've done on this series really prove that. But here we're actually going to configure in the BGP routing protocol, because EVPN is a sub-family member of BGP, and the BGP is massive. It's what makes the internet work. Here we're actually going to configure how can we configure EVPN in the Juniper Junos devices in this particular spine-only deployment. And once we've configured the EVPN, guess what? We're then going to configure the Virtual Extensible Local Area Network, the VXLAN. And again, this is all going from spine 1 over to spine 2, and vice versa in the opposite direction. And finally, step 8, we are then going to validate that everything that we have just done is working. We're going to go into the routing tables, we're going to go into the EVPN table, we're going to go into the VXLAN table. We're going to see is all this information actually being shared, advertised over that layer 3 connection, that adjacency from spine 1 to spine 2 and spine 2 to spine 1. So that is our plan of attack, that is our plan of configuration. What I suggest at this point, let's actually just get straight onto the Junos, straight onto the devices when they finish booting up, and let's actually do this configuration. And here we go. And as you can see, I've actually just wrote down all the different steps 1 to 8 in terms of what we're going to configure before we get to the validation process. But initially we're going to start off with step 1, deploying the underlay. So the underlay is the underlay routing protocol, the IGP. And as I said, this is going to go between spine 1 to spine 2, and that's going to be using open shortest path first in area 0. And also, just for your information, I've also entered in the information for ESI, Ethernet Segment Identifier 0, and ESI 1 in terms of those hexadecimal values, those 10 hex values, and what the system ID is when it comes to LACP. We'll move on to that in a few minutes. But also you can see I've actually added in the aggregated Ethernet bundles on leaf 1, so AE0 on leaf 1, and across on leaf 3 we've got AE1, AE1. So these are obviously the same pairs going up, or they will be the same pairs going up to 2 different switches, but the leaf devices will see that as the same switch. But hence they're both in AE0 or AE1. But if you look at those adjoining interfaces on the spine devices, they're either ESI0 or across here ESI0. But on these interfaces going down to leaf 3, we've then got ESI1 and ESI1 here. So a little bit more information, and I've also just added on the loopback 0 addressing and the autonomous system number for those spine devices to build that overlay. But one step at a time, let's actually start configuring OSPF. And here's my secure CRT. That's what that network symbol is. This symbol just here, this globe is just a virtual bridge, which allows me to remote secure shell into my virtual machine, my bare metal server from my laptop, if you're just wondering what that is. But before we actually configure anything on Spine 1, there's one or two things that we really need to do in terms of configuration before we configure OSPF. The first thing we need to do is to find a router ID. You can see just above Spine 1 that the router ID for Spine 1 is 1.1.1.1, and for Spine 2 the router ID is 1.1.1.2. And I've just highlighted those for you, just so you can see where I'm actually referring to. But we need to configure that for OSPF because OSPF needs a router ID, so it knows who's advertising those LSAs in the first place. So let's go into the command line interface, into configure mode. Very easy to do. We just go set routing options, router ID, and this is for Spine 1. That's 1.1.1.1, and there we go. Whilst we're also here, we need to check on the interface. So if I do show interfaces, you can see we've only got the management interface that I'm using to secure shell into. But we can also see we need to enable the GIGI000 interface between Spine 1 and Spine 2. So let's create that interface. So let's do set interfaces GIGI000.0 family inet address 192.168.10.1/30. There's a spelling mistake there. It is a /30, not a /31. Now we've got the interface actually defined. So let's now define the routing protocol OSPF. So let's do edit protocols, OSPF. Let's do set area 0. My typing is terrible today. And we need to define the interface that we are configuring into the underlay. So here I'm going to say GIGI000.0. Important to include the .0 or the .10, .500, whatever it may be, because we're using that to build the connection, the adjacency between the spines. If you omit, i.e. don't include the .x, whatever that x may be, Junos automatically assumes that it's .0. In this case, I am using .0, so that's perfectly fine. And now I'm going to say the interface type is point-to-point because this isn't a broadcast network between Spine 1 and Spine 2. And I will also include the interface loopback 0.0, and I'm going to set this to passive, i.e. I want to advertise this into OSPF, but I do not want to send LSAs out of that interface itself, which is only a loopback interface anyway. And on that note, I didn't actually create the loopback interface within the interfaces. So let's do top set interface loopback 0.0 family inet, and we could see the address just above the root ID for Spine 1 is 200.10.20.1/32. And let's do a quick show, just make sure I'm happy. So what I've got now is my underlay, OSPF, area 0, interface gigi000.0 with interface type point-to-point, because it is a point-to-point link. And I'm also advertising passively the loopback 0 into this configuration. So now if I just go top and do a quick commit check, and it's run successfully in terms of checking the configuration. Now one trick I'm going to show you is if I just do a show protocols OSPF, pipe display set is going to give me all the configuration that I've just done for OSPF. And the reason why I'm doing this is because I'm actually going to copy this. I'm going to cheat a little bit and I'm going to paste that onto spine 2 because we need the same area, we need the same interface, it needs to be the same interface type, and we need the loopback 0 interface as well. So let me just commit to the configuration on here and go over to spine 2, go into the command line interface, go into configure mode, and I'm going to paste that. And now if I just do show protocols OSPF, there we go. Exactly the same configuration. Just save yourself a bit of time. But we can't forget to define the routing options for the router ID. So for router ID for spine 2 is 1.1.1.1 or 1.1.1.2. Apologies, too many ones there. So that's my router ID now configured. Again, I need to define the interfaces. So let's do set gigi 000.0 family inet. We can see the address is 192.168.10.2/30, and I'm not going to forget to do the loopback 0.0 family inet address 200.10.20.2/32. Let's do a commit check, and that succeeded. And I'm now running that commit into the configuration. Spine 1 has committed it successfully. Let's come back to spine 2, and it's also done the commit successfully as well. So we now need to check, do we have the OSPF adjacency? So let's do run show OSPF neighbor, and we should see the link as full. Yep, there we go. It's a little bit off the display, so let me drag it over. There we go, that's just about there. So we can see 192.168.10.1, that's spine 1, out of the gigi 000 interface, and the adjacency is full, and it's coming from the root ID 1.1.1.1, i.e. everything about spine 1. Great, but what I now want to see is, can spine 2 see the loopback 0 interface that is on spine 1 at 200.10.20.1. That's important because we need that reachability for step 2 when it comes to deploying the overlay. So let's do run show root, and there you go. Here you can actually see 200.10.20.1/32 has been learned via OSPF. So it's in the routing table, but can we ping it? So let's do run ping 200.10.20.1 from the source of our own loopback address, which is 200.10.20.2, and a spelling mistake there, 20.2 at the end, not .1, and there we go, we've got connectivity. That is step 1 completed just there. So we have just done configuring the underlay with OSPF, and we've checked, we've validated the OSPF is up, it's full, it's working, and that we have reachability for the loopback 0 interfaces on each of the spines to and from each other. Now we can move on to step 2, deploying the overlay. So I'm just going to come back to spine 1 now. There's one more thing that we need to do right now in terms of step 2. There'll be a few other things coming up, but we need to define the autonomous system in the routing options. I could have done this in step 1 when I went into the routing options and defined the router ID. So let's do edit, actually let's just do show routing options. There you can see the router ID I configured in the last step. So I could have done this here as well, but I'm breaking this down into logical steps. Of course I could have done this command, set routing options autonomous system, at the same time. Of course I'm not arguing against that. But the autonomous system number, as you can see for spine 1, is ASN 65100, 65100. Yeah, I'm terrible with my numbers today. I don't know what is going on. But there is my autonomous system for spine 1. Now we need to have this IBGP peering between spine 1 and spine 2. So let's go into edit protocols, BGP, and let's create a group called edit group, and we're going to call this the overlay. Now we need this to be IBGP, internal. So to do that we say set type internal. We also need to define what is our local address. We need to do this because with the loopback 0 interface, we've got these .x's, these .sub interfaces, these .units. and there is X amount that you could have in terms of those units or sub interfaces on that one loopback interface. So we need to be very specific here, because every sub interface or unit can have a different IP address or IPv6 address or even an ISIS address. So we need to define 200.10.20.1, that is the loopback 0.0 interface. And now we're actually going to define who are we peering to, and that is spine 2's IP address. So 200.10.20.2, that is the IP address of spine 2's loopback 0 address as well. And let's do a quick show on here, and let me just go up one actually and do show again. So what you could see here is I've just created this group called overlay. It's type internal. This is my own loopback 0.0 address, and this right here is spine 2's loopback 0.0 address, and that's why we tested reachability in the last step, where I pinged from the spine's loopback 0 interface to the destination's loopback 0 interface. But what we also need to do at this point is define a family for IBGP. So when I say family, if I do set group overlay family and hit question mark, this is really cool. See all the different family members that you can define for BGP. So we've got EVPN, of course we're going to be doing that, but we've got INET, specifically IPv4. We've got INET BGP multicast. We've got, I don't even know what, INET MDT, multicast distribution tree. Wow. MVPN, VPN, INET 6, that's IPv6. We've got layer 2 VPNs. There's a lot here. So if we just do, just for example, set family INET, hit question mark again, we can now say, is this INET IPv4 multicast traffic? Is it using some kind of transport NLRI? Or are we using unicast, which is actually what I want to include. But we also want to do set group. Let me do the same command almost, but with the family EVPN. Now it's not enough just to say set family EVPN in this BGP group, because if I hit question mark, you can see you can apply it to a specific group. But we do need to say we want to signal this EVPN. So if I just do a quick show, what we're defining here is that we are using INET unicast traffic to exchange the updates, but also it's okay for spine 1 to send and receive family EVPN as that signaling protocol. EVPN, don't forget, is a control layer signaling protocol. It's advertising all that network layer reachability at the control plane. That was the word, control plane, not control layer, but the same thing. So we have to define within that group, for the overlay in this case, that we are absolutely using family EVPN to exchange that reachability information to these neighbors, only one in this particular case, and this is the source we're actually doing it from. These are important because the way IBGP works, or BGP in general, is when you're sending those different messages, those keep alive, those updates and notifications, etc., is expecting within the BGP messages, the packets to have this particular source address and this particular destination address. And if those don't match, the JSON sheet is just not going to work. It's probably going to be torn down. So let me just do a quick commit on this. And I'm not worrying about that BGP license. I've tested this. I don't know why it's giving me that, to be honest. BGP is most certainly there, but you know, we'll see. But spine 1 is now configured. I now need to do the same on spine 2. So let's do set routing options. Do not forget about the autonomous system number. So 65100. And now we can go into edit groups. Let's not edit groups. Let's do edit protocols BGP. Let's set the group overlay. Let's call it the same just to be consistent. And that is going to be type internal for IBGP. I'm going to be using the local address of spine 2's loopback 0.0 interface. That is 200.10.20.2. And I'm going to spine 1's loopback 0.0 address, which is 200.10.20.1. And let's see if I can get in the same line. I can also do family INET unicast as well. Let's do a quick show. And there we go, in one line. I'm quite impressed by that. I managed to configure all of that information there. I did actually configure the family INET unicast within that specific neighbor. There's different levels of hierarchy you've got within BGP as a routing protocol. But that's fine, that doesn't matter. But if I now just do set group overlay family EVPN signaling, and just do a quick show on that again, and there you go, you can actually see it's not included within the neighbor command, it's actually just outside of it, it's actually at the group layer to use EVPN as that signaling protocol, again to exchange that reachability information. So let's run this configuration, let's commit to this, and there we go. So what we should now see is the adjacency up between spine 1 and spine 2. So let's do a run, show BGP summary, and I'm just going to run the same command again because it's a little bit off screen actually. I just want to increase the screen a bit. Actually, there we go. You can just about see it there. I managed to get away with it without doing the same command again. So it has been established. Established is the BGP terminology for the same as OSPF when it says full, but in the BGP world we call it established. It's the final step in establishing, hence establish that BGP connection, where we go from down to established and multiple steps in there. But really, in a nutshell, we want to see established. And we've got it going to Autonomous System 65100. Already some packets have gone in, some packets have gone out, and this is the neighbor address here. Now, if I actually do a show route at this point, run show route, you're going to see that there is no new information. That's because we're not actually, we haven't defined the EVPN routing protocol yet. Only in step 2 have we actually configured BGP to use EVPN, but we haven't configured EVPN yet. That's why it's all the way down here at step 6. The next step though is actually defining the link aggregation groups on the leaves and the Ethernet segment identifiers on the spines. But for now we can actually see that we've got adjacency in terms of overlay between spine 1 and spine 2. That's exactly what we want, so we could say yep, step 2 is done. Okay, and here we go for the third step, which is we are going to build the link aggregation group interfaces on the leaf devices first, specifically on leaf 1 and leaf 3. And then we're going to build, it's really a sub-step, 3B, we're going to build the Ethernet segment identifiers, ESI 0, ESI 0, and ESI 1, ESI 1. On those spine devices. So that's important because, and as I've said already, from the leaf devices, that it just sees these as aggregated Ethernet, but from the spine devices, it of course sees these as different Ethernet segments, obviously with an identifier on the end. Hence, we need the way to define what are these 10 hex values, which you can see I've actually just wrote here. Well, there's always a reason to my logic, so that's why I wrote the ESI values here, as well as the system IDs. The system ID has to match from spine 1 to spine 2 for that same Ethernet segment bundle. By doing so, what it will do is it will make leaf 1, as I'm highlighting here, think that it's connected to the same upstream system, the same upstream switch. So we use an LACP to fool, to trick the leaf device into thinking, oh, I'm connected to the same upstream, and I can use the same aggregated Ethernet bundle to get to that same switch, that same system. Great. So pretty cool, but this is what we're going to do first, is actually configure the aggregated Ethernet on the leaf devices and then move onto the spine devices. And so let's go straight onto leaf 1 and let's go into the command line interface, into configure mode. Do not forget this configuration. If you forget this configuration, you will define the interfaces to be aggregated Ethernet and it will not work. I can promise you this has caught quite a few people out, including myself. So if we do set chassis, aggregated devices, Ethernet device count, and from leaf 1, it's only got one AE bundle, which is AE0. So we only need to do the 1. That is the command that a lot of people forget. And now we could go into the interfaces and configure GigE001 and GigE002 to spine 1 and spine 2 respectively to be part of the AE0 bundle, and configure the AE0 bundle itself. So let's do set GigE001 to spine 1, and first we're just going to say ether options 802.3 AD AE0 done. Going to do exactly the same for GigE002 802.3 AD AE0 done. And now we can define the aggregated Ethernet bundle itself. So first I'm just going to do unit 0 family Ethernet switching. Now I'm going to do interface mode trunk, VLAN member, and I'm going to say V10. I haven't created V10 just yet. I'll do that in just a second. It's members V10. So if I just do a quick show AE0 so you can see what I just configured. So I've just done unit 0 to be a trunk interface and to only have VLAN members V10 for VLAN 10. But what I also have to do is I have to define this to use LACP. So if I do set aggregated Ethernet, aggregated ether options, LACP, hit question mark, and now you can see we could do passive, periodic, system ID. That's what we need to do on the spine devices. But just for here, I'm just going to say active. Let's do show AE0 again. And that is my aggregated Ethernet bundle actually configured. The only thing I just want to do here at the same time, let's just do set gigi000, which is going down to host 1.0 family Ethernet switching interface mode access, because it's an access interface, VLAN members V10. And just go to the top, I'm just going to quickly define that VLAN as well. So let's do set VLANs V10, VLAN ID 10. So if I do quick show VLANs, I've got my VLAN created. If I do show interfaces, gigi000, VLAN 10 is an access interface on gigi000. If I do gigi001, it's assigned to AE0, as is gigi002. And if I do show interfaces AE0, we could see that it's trunking only VLAN 10 up to or through the AE0, and AE0 has LACP, which is actively working. That's it at this point. I can now just run that configuration and go over to Leaf 3 and do exactly the same thing. So good recap here, good training, good repetition. Command line interface, configure mode, let's do set chassis, aggregated devices, Ethernet, device count 1, but this is for AE1 now, we must remember that. And let's first do set VLANs, V10, VLAN ID 10, just so it's there already created. And now let's go into the interfaces. Let's set the gigi000 interface, which is going down to host 2, unit 0, family Ethernet switching, interface mode access, VLAN members V10. Let's also define set gigi001, which is going to spine 1, ether options, 82.3 AD, AE1. Let's do the same for gigi002, which is going to spine 2. And now let's define SETI aggregated Ethernet 1, aggregated Ethernet options, LACP active. Let's do set AE1 unit 0 family Ethernet switching, interface mode trunk, VLAN members V10. And now if I commit that, we've got the aggregated Ethernet bundle configured on both Leaf 1 and Leaf 3. But if I just go top and do show interfaces, so what you can see here is gigi00 has got the access interface with VLANs 10. Gigi001 and 02 are configured to be part of aggregated Ethernet 1. And for the AE1, it's using LACP active, and the unit 0 again is set to layer 2 trunking with only VLAN members V10 to be trunked over it. So that is the first part done, but we now have to configure the ESI on the spine devices. And before we go any further, it's important to refresh yourself and remember that for the spine devices, as I said, they've got two aggregated Ethernet bundles. They've got ESI 0 and ESI 1. Same for spine 2, ESI 0, ESI 1. And again, those hex values are over here. So on spine 1, let's go right to the top and let's do that command that we must not forget. Set chassis aggregated devices Ethernet device count, and we want 2, not 1. And now let's go into the interfaces. Let's do edit interfaces. Let's set the gigi001 to be part of ether options 82.3 AD AE0. Note it's pointed down to AE0 there. And we'll do the same, but for gigi003, which is going down to Leaf 3, to be 82.3 AD AE1. Great, so, but now we need to define those aggregated Ethernet bundles as well. So let's do set, or let's actually do edit AE0, and now I can configure it all from here. So first, let's actually define that Ethernet segment identifier. How do you do that? Well, let's just do set, hit question mark, and right about here, you can actually see the ESI configuration of a multi-homed interface. So that's what we actually need. So let's do set ESI, hit question mark. This is something that I've literally just learned, and I think this is so cool. We can auto-derive the Ethernet segment identifier. And we could do so if I just do auto derive. I'm not going to do this and hit question mark. We could do so using different types or different ways. We could do so via LACP. So we can actually do a type 1 LACP or a type 3 system MAC. I think that's really, really good. So we could actually use LACP to identify what the ESI actually is. That's pretty powerful, but I want to look into that a little bit more. But for now, all I'm going to do is do set ESI, and then I'm going to enter in the ESI value, which is all the way up here. This 00 has to start with 00, and then 8 hex values of all 01s, and right at the end 11. So let's do 00, 01, 01, 01, 01, 01, 01, 01. I've lost count. And last one, 11. It's quite a big number to write out in all honesty. But now if I do the same set ESI, and now we're going to define what kind of redundancy do you want it to be. Do you want it to be all active or active standby? I'd imagine in most cases you want it to be all active. So now I'm going to define ESI all active. Let's do a quick show. You can now see I've defined that Ethernet segment identifier. But we need to go quite a few steps further because I've still got to configure the LACP system identifier to basically trick these downstream devices to thinking they're actually connected to that same upstream device. And to do that, we actually just do set aggregated Ethernet options LACP. First, I'm just going to say it's active. And if I just hit back up, I can now define what the system identifier is. And it's almost like a MAC address in terms of the bytes that it's long. It's 6 bytes long. But you can see I've configured it to be AA, BB, CC, DD, EE, and right at the end 11. Hopefully that's a correct format. And now I could define the aggregated Ethernet 0 bundle to have a unit 0, family, Ethernet switching, interface mode, trunk with VLAN members V10. Now at this point we of course need to configure V10 on the spine as well. So let's just do set VLANs V10, VLAN identifier 10. Let's do a quick commit check on this. And that's it. We have now configured our AE0. I'm not going to configure it or commit it just there because we need to do the same for AE1 on spine 1. So let's now go back into edit interfaces and let's do AE1. So it's going to be a bit quicker now. So let's do set Ethernet segment identifier all active with this particular hex of value. So it's now going to be 000 colon 02 02 02 02 02 02. I'm going to have to count this. And there we go. That's 9. And right at the end, we've got 2 2s. That's our 10 hex values. Now I can also define the set aggregated Ethernet options LACP system identifier, which for AE1 is going to be AA, BB, CC, DD, EE, and 22 at the end. And of course I need to define LACP to be active as well. And now I can define set unit 0, family Ethernet switching, interface mode trunk. And let's do set unit 0, family Ethernet switching, VLAN members V10. I can't remember if I configured the VLANs. There's obviously quite a few configurations here. So let's do top show VLANs, and yes, I did. So let's do a quick commit check on this. And that's it. So I'm just going to commit that configuration, and then we're going to go over to spine 2 and pretty much do exactly the same thing. And so let's go on to spine 2. Let's go to the top and let's do set chassis aggregated devices Ethernet device count 2. And let's also create the VLAN whilst we're here. So let's do set VLANs V10, VLAN ID 10. And let's go into edit interfaces. And let's do set GigE 001, which is going down to spine 1, ether options 82.3 AD AE0. And let's do set AE1 to GigE003 to leaf 3. And let's now define edit AE0 for aggregated Ethernet 0, of course. Let's define the Ethernet segment identifier first. And actually, let's just do all active. Let's get that done. It's a nice, quick, easy command. And now let's define that 0, 0. I always do that. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1. I think that's correct. I'm going to count. That's where that auto derive will really come in handy. Every single time I'm doing that, I'm having to stop and count. You know, it takes a bit longer. But that's the Ethernet segment identifier basically defined. Now I need to define the LACP. So let's do set aggregated Ethernet options LACP. Let's do active. And also let's now define that system identifier. So system identifier for AE0 is AA, BB, CC, DD, EE, 1, 1. And let's do a quick show. And that is my, I forgot unit 0. Thought I was forgetting something. Set unit 0, family Ethernet switching, interface mode trunk with VLAN members V10. Let's do a show again. And there we go. I've got my ESI defined. I've got my aggregated Ethernet options defined to use LACP with this system identifier. So now spine 1 and spine 2 have the same system identifier. And thus, for AE0, which is going down to leaf 1, it's going to think it's connected to the same upstream device because they're sharing this common system identifier. And we're trunking only VLAN V10 over this particular interface. And of course, GigE001 is assigned to AE0. Need to do the same for AE1. So let's do AE1. Let's define ESI all active. So just all active multi-homing. So both links can be used. Let's also define that glorious number 02, 02, 02, 02, 02, 02, 02, 02, 2, 2. Yeah, I'm going to look into that auto derive function. That looks a lot better. But now let's set the aggregated Ethernet options LACP active and the LACP system identifier for AE1 is AA, BB, CC, DD, EE, 2, 3, 2, 2. And it's to set unit 0, family Ethernet switching, interface mode, trunk, and I want to have VLAN members V10 associated to this. So let's go to the top. Let's do show VLANs. I've got my V10 created. Let's do show interface GigE001. That is assigned to AE0. GigE003 should be to AE1. Let's do show interfaces AE0. I've got my Ethernet segment identifier, LACP with that system ID active with that unit trunking. And let's do the same for AE1. And exactly the same, but obviously a difference in system ID and ESI. And that's it. I'm now going to commit that configuration. And we have now very quickly just done steps 3 and 3B with the addition of actually configuring the VLANs as well. So we've now got the VLANs going down to host 1 or to host 2 from leaf 1, leaf 3 respectively. But we've also configured the aggregated Ethernet bundle on the leaf devices. At the same time, we've configured the ESI. It's a bit difficult to draw here actually, but we've configured the ESI on the spine devices to have these particular AE bundles with this system ID for each AE bundle and with this hex value as well. Pretty cool, pretty easy to configure. So let's do a quick recap. We have built the OSPF underlay going from spine 1 to spine 2. On top of that, step 2, we built the overlay using IBGP with the EVPN signaling to go on top of the OSPF. And we had that loopback 0 information actually advertised in the underlay, and thus IBGP was able to get the adjacency. But the EVPN signaling, again, this isn't configuring EVPN, it's just saying, hey, Mr. IBGP, I want you to use EVPN to exchange network layer reachability information. And then on the last step, we configured the link aggregation group and the AE ESI on the spine devices as well on the Leaf 1 and Leaf 3. Now what you can see that's new here is I've added in the VNI. So on step 4, so we're actually going to configure the VLANs and VNIs. I got a bit ahead of myself in the last step. I configured the VLANs, but you know, we're all human, doesn't matter. But now we need to configure the VLANs, which has already been done, but actually associate those virtual network identifiers, which is what VXLAN uses to identify that tunnel, that needs to be associated to a VLAN. Hence, I've entered this in here so you can see VLAN 10 is being associated to virtual network identifier or VNI 5010. Now we do these configurations on the spine devices, not on the leaf devices, because all the leafs are doing are actually sending up that tagged traffic up to spine 1 and spine 2. We've got all that EVPN, or we will have all that EVPN and VXLAN tunneling between spine 1 and spine 2. So obviously it then stands to reason we've got to configure this step on the spine devices. So on spine 1, let's go top, edit VLANs, do a quick show, and we can see VLAN 10 there. The configuration first is extremely straightforward. Let's do set V10. And then if I hit question mark, you can see right at the bottom is this lovely VXLAN. So let's do VXLAN, hit question mark again so I could talk you through it. Here is our VNI. Note the extraordinarily huge value, 16,777,214. Wow, that is quite a lot. But also note this other part that we do want to keep or put into this configuration. Ingress node replication. This is for BUM traffic, broadcast unknown unicast and multicast traffic. I.e., if BUM traffic is received on spine 1, it's going to copy that and send it to all interested parties, and spine 1 will know who's interested via a particular EVPN route type 3. If you don't know what that is, just check out this link. But we need to enable set V10 VXLAN VNI, and let's give it the value of 5010. And I also now just need to do the ingress node replication to say we are copying all of that BUM traffic and distributing that over the underlay, or using the underlay. We're just copying and sending out. And now if I do a quick show, that's it. But note I've now got quite a few warnings saying, oh, you need a VTEP source interface and I require a license. I'm sure I don't need that. Also, I need to do some kind of management. That's where EVPN comes into it. That's okay, that's fine, and that's correct, because in the next few steps is where we start configuring VXLAN and EVPN, and those warnings are actually going to go away, hopefully. But let's go into spine 2. Let's go into edit VLANs, do a quick show, and do the same configuration. Set V10 VXLAN VNI 5010. Can I do it on the same line? Yes, I can. Ingress node replication, do a quick show, and we've got the same warnings, the same error messages, so I can't commit it. But don't worry, we're going to work through this. And here we go. You can now see we've done options or steps 1 to 4, and now we're right here configuring that Anycast gateway. The Anycast gateway is really what's referred to as a distributed gateway, and you can also see that I've added in some new information just here. Don't worry, I'll go through that in just a second. But why do we need this Anycast or distributed gateway? Well, what we've done so far, it really in the last step 4 I think it was, is we configured our virtual network identifiers, and we associated, as you can see here, VLAN 10 to VNI 5010. And that's fine, that's great. But this is really providing that layer 2 connectivity. If we look at it from host 1, this is in VLAN 10. If we look at host 2, this is in VLAN 10. And as such, all that traffic can just be trunked from, say, leaf 1 to spine 2 and down again. But what if on leaf 2, and I've left leaf 2 alone during this video, but what if there was another host here, another server, and this was in VLAN 20, just for example? How is traffic from host 1 going to go through whatever spine down to this server and onto VLAN 20? Well, obviously in just a layer 2 trunking scenario, that's not going to happen. And that's why we need this Anycast or distributed gateway, because with that gateways, we're having that layer 3 functionality, i.e. our inter-VNI, our inter-virtual network identifier routing. So we do need this capability to provide that inter-VNI routing. But why do we need this virtual IP address? And optionally, it is an option, but a virtual MAC address. There has to be a virtual MAC address there, but it's optional for you configuring it. Why do we need that? Well, in the data center, these devices, they're virtual machines, pretty much. They're hosted on some type of hypervisor, sitting inside some very beefy, powerful server. But these can migrate. So the virtual machine that's on host 1 can migrate over onto host 2. And without this virtual IP address, if before that device migrated over, if it was configured to have this physical IP address, which say was on spine 1 here, then leaf 2 or that server might not be configured or might not have those values in its routing table to get up to spine 1, just for example. And thus we need this virtual IP address split between and shared between the spine devices, so it's distributed across those spine devices. So no matter where these devices roam, whether it be from host 1 to host 2 or even from host 2 over to this new virtual machine here, that they've still got connectivity here. And there we go, making the screen look a lot less busy. And the way we do that is we define in the Junos world an IRB. So on spine 1 we'll have an IRB.10 for VLAN 10 for VNI 5010, and we have an IRB.10 here as well on spine 2, and they will have their independent own physical IP addresses, which is aligned to that IRB, the integrated and routing bridging interface. But underneath that, we can then define that virtual IP address and the MAC address as well. So I'm just going to write MAC here, and obviously the same over here for spine 1. And thus, if this virtual machine was to migrate over to the server host 2, it's still going to have connectivity. And that is essentially what a distributed gateway is. It's distributed across, in this case, your spine devices, because these are providing your layer 3 functionality. And within this, you've got your inter-VNI routing as well. And let's go on to spine 1. The configuration to do this is very straightforward. So as I mentioned, we need our IRB interfaces. So that's an interface. So let's go into edit. Oh, let's go to the top. I'm still in VLAN. So top, edit, interfaces, and let's set IRB.10 family INET, and it's to find that physical IP address for spine 1, which is 10.20.30.254/24. And let's not forget the address as well. And there we go. But if I just go into IRB.10, we can now define under this, if I hit question mark, I just made a little bit of a pig's ear of that, so let's start again. So let's do set unit 10 family INET address, and now you could see here it was on the end. That's where I made a bit of a pig's, a mess of that. But under, and actually I'll just hit back. So after you've entered in the IP address, you can then see here is where we could define that virtual gateway address. So I've just entered in the physical IP address of the IRB.10 on spine 1. Now I can enter in the virtual gateway address, and that's going to be 10.20.30.1. And now if I do show on the IRB, we can now see here's IRB unit 10 with this physical IP address as such, but with this virtual gateway address. This is what's going to be distributed. But as I said, it is optional, but we also ideally want to define the virtual MAC address as well. So if I do set, then right at the bottom, right here, we could see virtual gateway v4 MAC address. So this is a MAC address for IPv4 packets, or you can define a v6, which is a MAC address for IPv6 packets. I don't know if the MAC address is different. I'd have to look into that in terms of IPv4 versus IPv6, but it doesn't really matter anyway. So let's do virtual v4 MAC address. And as per the sheet, as per what I've defined, I'm just going to do 01, 02, 03, 04, 05, and 06. Let's do a quick show on that, and there we go. Okay, so apparently, new news to me, it doesn't like 01 at the beginning, so I've changed it to 00, and you can see that there. So there is that new virtual gateway v4 MAC address. But it's not enough to just define an IRB interface. Yes, that's great. It's got its physical IP address, and it's got its virtual gateway address, and it's got its virtual gateway v4 MAC address. But we need to associate that IRB interface to the VLAN, because the VLAN is associated to a VNI, to 5010. And if we associate this IRB interface to that VLAN, it's thus associated to that VNI. So let's go to the top. Let's edit VLANs, do a quick show. We can see here's VLAN V10 here with VNI 5010 using ingress node replication. And what I'm going to do is I'm going to do set VLAN V10 layer 3 interface IRB.10. Do a quick show on that. And we can now see we've just configured our layer 3 interface with that virtual gateway MAC address, virtual gateway IPv4 address, and that physical IP address as well to be associated to this VLAN 10, and that is referenced to VNI Virtual Network Identifier 5010. Again, I can't commit it because of all these errors, but they will go away. But I need to do the same on spine 2 now. So let's go to the top, edit interfaces IRB, and let's do .10, and let's do set family INET address 10.20.30.253/24. And now we define the virtual gateway address to be the same 10.20.30.1. So that's the same virtual gateway address that we just configured on spine 1. Now I define the set virtual v4 MAC address, and it started with 00. I've learned from that. 02, 03, 04, 05, 06. Let's do show. And there we go, exactly the same. The only difference really is that we've got 253 on spine 2 and spine 1 has got 254. But that gateway address is absolutely the same as is that v4 MAC address, and thus we could distribute this across spine 1 and spine 2. So if hosts move or if a link goes down, everything is still reachable. But coming back to it, we have to go into top, edit VLANs, do show, and let's do set VLAN V10 layer 3 interface IRB.10, do show, and we have now configured our Anycast gateway, our distributed gateway, but we cannot again commit to this configuration just yet. And here we go, we're finally on step 6 where we're starting to configure EVPN. Next step, we're going to configure the VXLAN tunneling. So we've done a lot of the pieces of the puzzle in terms of the link aggregation group and the Ethernet segment identifiers and the chassis, the underlay, the overlay, the VLANs, the mapping of the IRB to a VNI through the VLAN, etc. So there's a lot of things that we've actually gone through. Now, fortunately, if you know EVPN, the next few steps is really where everything starts coming together. So all we need to do now in terms of step 6, configuring EVPN, is actually go into the EVPN protocol and say, what are we encapsulating? Because EVPN and VXLAN are two different protocols. EVPN doesn't have to work with VXLAN. You can have EVPN working with other protocols such as multi-protocol label switching if you're in a service provider environment. And also MPLS doesn't have to work with EVPN. There's other types of control signaling protocols out there like LISP-P, or LISP-P I think it's Location Independent Separation Protocol, something like that. My point is there are two different protocols, and we need to define under EVPN who are we working with, what protocol are we working with in terms of the data plane technology. So let's go into protocols, let's go to the top, edit protocols, EVPN, do show, and obviously there's nothing configured there. But if I do a quick set and hit question mark, you can see there's quite a lot, and I'm just going to make this a bit bigger because this is really important. You can see there's quite a lot of options that we can do here. So we can say encapsulation. This is the first command we're going to do. We can do VNI options. We could do trace options. I'll come on to VNI in just a minute or so. We've also got this no core isolation. This is very important. We do need this in a spine only deployment. I will come on to that as well. But for now, let's just do set encapsulation, hit question mark, and note the different types of data plane technologies that EVPN can work with. So in this case, we are working with VXLAN. I'm also going to do, just quickly set no core isolation. And also the other important thing that we need to define is the multicast mode. This is important because we need to define for EVPN how you're going to handle bum traffic, as I was saying before. So if I do multicast mode, hit question mark, there is only ingress replication because Juniper Junos only supports ingress replication. And if I do a quick show, yeah, it's saying, oh, hang on, you need a virtual switch and you haven't configured, you need to configure more. Don't worry, it's coming, this will be resolved. But we've got our no core isolation, we've got our encapsulation, so we're encapsulating all of that data plane traffic into VXLAN tunnels. And if there is bum traffic, because this would be unicast, if there is bum traffic, yes, it's going through a VXLAN tunnel, but we're going to use ingress replication as well. But what is this no core isolation feature just here? Well, in a spine-only model, what we've got here, as we know, the layer 3 functionality is established between spine 1 and spine 2. Everything from the leaf devices up is layer 2. Okay, so that obviously implies that this is the core. This is where all the magic, the inter-VNI, etc. routing is taking place. But what happens if this link goes down? If this link goes down, the OSPF adjacency that's built over this link is torn down. It naturally goes down. The IBGP pin for that overlay naturally goes down as well. The EVPN signaling that goes over this also goes down. Now, without the no core isolation setting, what would happen is both spine 1 and spine 2, to stop any traffic going to and from these links, this link, is it would just disable this link. It would disable this link. You would disable this link, disable this link, disable this link, disable this link. And as such, any traffic that wanted to go east to west or north to south across your data center suddenly cannot do so because all of these interfaces here are just disabled. You obviously do not want that. That is not going to be ideal. Hence, if you've got a spine only, highly recommend you look into this feature. Obviously, per use case, please investigate this, due diligence, etc. But definitely no core isolation in a spine only model could be of significant value in such a scenario. But coming back to spine 1, what I also want to do is set the VNI options. Now under here we can actually then define what the virtual network identifier is, I5010. So yes, we're encapsulating our data plane traffic through VXLAN tunnels, but now we're defining specifically this is for virtual network identifier 5010. What we can now define as well is a VRF target, the virtual routing and forwarding target. This is important because there's an export and import policy with VRF targets. And here we are defining an export policy. The receiving VTAP, the receiving leaf device, if it doesn't have the same import policy in terms of that target, it's just going to discard those packets. So let me do target, VIF target, I should do, then do target, and then we got to enter in a particular target. So here I'm going to do 65100 for the ASN that we're working in, and this is for 10. And now if I do show, you can see I've configured my VNI options here, and for VIF target, etc. There. Now the important point I'd like to highlight to you is that this is for route type 2 and route type 3 only. So if you're wondering, well, what about route type 4? Well, route type 4 doesn't go past those leaves anyway, though if it's in a multi-homed environment. So we don't need to worry about route type 4. What about route type 1? Well, the route type 1 isn't applied here, it's actually applied in our global switching options, where you would have a globally configured VRF target, and then that's exported. And if the receiver's got that same VRF target as an import policy, it would then receive all those route type 1s from this particular spine device or leaf device, whatever it is, and import all those Ethernet segment identifiers into its routing tables. But in terms of configuring EVPN for this, we've done our VNI options for 5010, for VNI 5010. We're saying we want to encapsulate VXLAN, we want to use ingress replication, and, where is it? No core isolation as well. So let's go into Spine 2 and do exactly the same. So let's go into top, edit protocols EVPN, and let's do set encapsulation VXLAN, no core isolation. Can I do it all in one line? Oh, look at this. Multicast mode. I love that. Ingress, no ingress replication. Can I also do the VNI options? That would be great. Oh, that's brilliant. VNI options, VNI 5010, VRF target, and here I'm going to define 65100 colon 10. Let's do a quick show, see if I got that all right. Yeah, there we go. So I'm actually I'm quite happy with myself there. I'm surprised it was all on one line. But no core isolation, as discussed, we need that. We need to encapsulate all the traffic into VXLAN tunnels. For bum traffic, we're using ingress replication. That's only supported on Juniper Junos. And for the VNI 5010, we are using this VRF target of target 65100. That's the ASN for VLAN 10. It's just an arbitrary number here. That could absolutely be anything. But that's how we configure EVPN. And so now we're on to the last part of configuring the VXLAN. Hopefully at this point, once I've done this, all these error messages are actually going to disappear. But we'll see, you know, fingers crossed kind of approach. Now to do this, it is very straightforward. Is actually we go to the top, because I'm in protocols EVPN right now, and let's do edit switching options. And there's a few commands here that I've talked about over quite a few videos that I've left out till now. Specifically, we've got to look at what is our VRF target. Now this is at the global switching options. This is something that would be overwritten by the VRF targets that I just done in the EVPN protocol. But that was only for route types 2 and 3, for that MAC advertisement and for that ingress bum traffic, whatever that route type 3 is actually called. It's not for the route type 1. Hence, we have to define here within the switching options, our switch options here, what is that global VRF target? Because if we don't have those VNI options defined in that EVPN protocol, they're all going to adopt for route types 1, 2, and 3 this global VRF target. But we also have to look at defining, here it is, this really nice route distinguisher as well. And of course, what we're using for our VTEP source interface. Without this, the VXLAN tunnels do not know where they're going to build that tunnel to or from, in terms of what is that source loopback 0 interface. But first, it's define that route distinguisher. And if I hit question mark, you can see this is the format. So you can either do a type 0 or type 1. I quite like the type 1, which uses the format of, let's take the router ID and then colon actually have some kind of arbitrary number. So for here, I'm going to do 5010 for VNI 10 as well. Then we have to define our VRF target as well. So just like I did before, I'm going to define this to be 65100 colon 10, just to keep things consistent. And now I'm going to define what is my VTEP source interface. Here question mark, and you can see I've got my loopback 0 interface right here, and that's what I am going to use for the configuration. And now if I do a quick show, at this point I'm hoping, and the VRF target didn't take for some reason, so did I do something wrong? Let's have a look. Yeah, silly me, it's literally telling me what it is. I forgot the keyword target, so if I hit up, it's not enough in Junos just to say VRF target, and then that target itself. You have to then define the target colon 65110, I think it was. So if I do that now and do show, we can then see our VRF target here. So yeah, VRF target, and then these values isn't enough. You have to do VRF target, and then those numbers. And the reason being is so that Junos knows that this is the target that's pointing the way to those extended communities in that update message. So now if I just look in my other areas of configuration. Hopefully those error messages have disappeared. So let's do show VLANs. I am getting a warning here that requires the VXLAN license. I'm hoping that will disappear. I'm hoping that's not going to be an issue, but we will see. Let's do show protocols EVPN. Yeah, it's just giving me the same warning about VXLAN. Let's do show interfaces, and all the messages are gone there. So if I finish this off by doing a commit check, and there is one command I missed, darn it. That's why we do these, to the extended VNI list. So that is something that's actually inside the EVPN protocol. So let's just go into edit protocols EVPN, and let's set the extended VNI list, hit question mark. So we're basically defining here what VNIs do you want to participate within this EVI domain, and I'm going to do just 5010. Let's do a quick show, and we can see I've got my extended VNI list right there. And let's do that quick commit check again, and there you go. So it has now almost succeeded. It's now only telling me that you need a VLAN license. Honestly, I don't know if it's going to let me configure that configuration. In fact, let's do it now, because everything is actually done now on spine 1. So fingers crossed. No, it's already telling me that I need the VLAN license. But will it actually push it? It did push it. I'm really glad about that, because otherwise VXLAN isn't going to work. But we've now configured spine 1 to have VXLAN tunneling. Now let's go on to spine 2 and do the exact same configuration. However, before I'm in here, I'm still in the protocol EVPN. So let's do the set extended VNI list 5010. And let's go into the top and edit switching options. We need to define our route distinguisher. So that is going to use the type 1 of the router ID first, colon 5010. I'm also going to set our global VRF target. Do not forget to write target as well, colon 65110. And I'm now going to define my VTEP source interface as well. Hit question mark, and I'm going to define loopback 0.0. And now that should be the configuration on spine 2. So let's go to the top. Let's do show VLANs. Yeah, apart from the license, the error messages have gone. Let's do show protocols EVPN. Looks good. Let's do show protocols. Oh, let's not do that. And let's just do show interfaces IRB. And that looks good as well. So if I do a quick commit check, then hopefully it's going to pass apart from the VLAN license. I don't know why it's giving me that, to be honest. If it then commits it, doesn't matter. But let's commit that configuration. And that's it. We have now just built from scratch our underlay, our overlay, the ESIs, the aggregated Ethernets, the EVPN protocol, the VXLAN tunneling, etc., etc., the VLANs, the VNIs during this video. So now it's actually on to, can we validate that this is actually working? Okay, and so you can probably tell that the screen has changed because I have slept. It's a long video. So let's just log back into the command line interface now. Let's confirm that all of this is actually working as I just said. So first, let's just take it from an overview perspective. Let's just look at our BGP summary. And what you can see here is immediately, again, we can see it's established, but note we have got different tables now appearing. Not only have we got this inet.0, which is the master routing table for IPv4, but now we've got this bgp.evpn.0 table, as well as this default switch.evpn.0 table. And now you can actually see we are exchanging all of these packets between the spine 1 spine 2. So first 16 would be active, so there's been actively sent 16 updates. We've received 16 updates, and we've accepted 16 updates, but we didn't damp any, which is that last 0 there. So obviously that's good news. We didn't hide or discard any received updates. And if you're wondering what these tables are, the bgp.evpn.0 is all the BGP routes via EVPN that have been learned and received from a peer. So we'll go on to this table in just a minute, and the default switch.evpn.0, these are all the MAC addresses which have been learned both locally and remote. And this is called the default switch because by default, when you configure EVPN, it will just by default go into the default switches routing switching table, not routing switching table. That doesn't make sense, but the default switching table, specifically just the default MAC VRF. This is what this is referring to. You can of course create your own MAC VRFs, custom VRFs, but you'd have to do so in routing instances, and then you'd see those names of those routing instances here, and then you could do route leaking, etc., etc. But as you could see, we are sending and receiving. So let's go into a little bit more information. Let's first just do show route. Let's just do show route in general. And you can see here, here's the master routing table, inet.0. And if we scroll further down, we've then got our BGP EVPN.0. So I'm just going to hit space and let's just scroll back up. This is great. This is where practice meets theory. So this is a type 1. We've got the type 1 ESI route type. So this is about advertising an Ethernet segment identifier. How do I know it's a type 1? Well, it starts with 1 colon, and then we've got the actual route distinguisher here. So this is the route distinguisher of spine 1, where I configured 1.1.1.1. That's the route ID for VNI 5010. And here's the ESI that actually we configured. Note the ESI over here for ESI 0, that is matching here. And I know there's two different types of route type 1s, but this is the auto discovery route type 1 for the EVPN virtual instance. And we've got exactly the same, another route type 1 for the ESI 1. This is for ESI 0, this is for ESI 1. But note we've then received the same advertisements, the same ESI values from the spine 2, because I could see spine 2's route distinguisher here, and that's for both ESI 0 and for ESI 1. And if I keep scrolling down, we can then see the MAC-IP advertisement. So this is a route type 2. And then we've got the route distinguisher again, the VNI, and the MAC address, and .maybe the IP address that has been learned. We could see where it's been learned from. So to get to this MAC address, I can go through 192.168.10.2 via this GigE00 interface. If this wasn't a spine-only topology, and if you had multiple paths to spine 2, you would see those multipaths there, but you'd have to configure a policy option for that, export that into the forwarding table, and also configure multipath multi-AS within that BGP group. But don't worry, we're going to be doing that on the next video. But if I keep scrolling down, we could then got our type 4s, which is all about split horizon, a designated forwarder for that particular domain, for that broadcast domain. And then we've got our default switch. So this is where all those MAC addresses are actually learned and stored in the default switching table. So the BGP.EVPN.0 and the default switch EVPN.0, they are linked. But just remember that they are linked in the aspect that we've got our master routing table, we've got our default routing table, and then you can create your own custom MAC VRFs, and you can obviously reference them here. So in summary, that is working. I can also do show EVPN database and see all the information that is in the EVPN database. So I could see for the VNI 5010 that here are the MAC addresses that have been learned. So that's obviously one that we've configured. So that specifically is the MAC address of ESI 1. You can see that there. Here's the active source that has been advertised from, and it's come from 10.20.30.1. That is obviously the virtual gateway. So this is probably being advertised from spine 2. And I can also do show Ethernet switching table VXLAN tunnel endpoint. And at this point, you can say, well, I want to check, what's happening with the VXLAN for the Ethernet switching for the Ethernet segment identifier, or for the source for that VTEP, or for the remote. So let's have a look at ESI. And now I can see all of the ESI values. What is that remote VTEP's IP address? The IFL. So note Here is not the VNI, this is just a random number that is automatically populated for that virtual tunnel endpoint, automatically created, and any flags and the amount of MAC addresses that have been learned and advertised. Obviously there's quite a lot here, I'm not too sure what the flags are, but that's, and the VENH, that's probably a lot more studies there, but that is for the ESIs. You can also do it for the source. So let's have a look at the source information. So here is my VLAN 10 going to 5010. We didn't configure a multicast group IP address. Let's have a look at remote. And here's the remote as well. So remote VTEP, remote IP, sorry, for the VTEP is 200.10.20.2. For this VNI, no multicast group again, but it has this interface VTEP number. Now the real question is can host 1 actually ping across to host 2? And can it actually ping the default gateway, which is that virtual IP address? So let's go into host 1. I've already configured the IP address, and these are in the same broadcast domain. Both host 1 and host 2 are in VLAN 10. So first let's just do ping the remote end 10.20.30.20, which is host 2's IP address, and we're getting a ping. Can we ping the virtual IP address, that virtual gateway address that's on spine 1 and spine 2? So it's ping 10.20.30.1, and there we go. So what we have there is we've actually validated that EVPN is working, that we're getting routes installed into our routing table, into our EVPN database. We've checked the VXLAN tunnels, the source, the endpoints, and there's a lot of information that we could go through further. But this has been a long enough video, and we've just validated that host 1 specifically can ping host 2 and ping that gateway. So if spine 1 was to fail, it's still got connectivity to spine 2, or vice versa, because they've got that distributed gateway. And so that's it, everybody. I hope you found that useful. I hope you found that informative. Been a lot of information that we've gone through, and as I've always said through every part of this EVPN-VXLAN series, EVPN is a massive protocol. It really is huge, and there's a lot more configuration videos that are to come. And this video, this part, has really focused on how to configure a spine-only topology and what you need to be aware of in terms of that no core isolation, and really from a logical perspective, the steps to go through to get from non-working to actually validating is it working. Now, it's not to say that my approach is the best practice. That's what generally works for me, but I'm sure that everyone will find what works for themselves. This is obviously just a guide at the end of the day. But I hope you found that useful. Hope you found that informative. If you like this video, if you like this part, please give me a thumbs up. It's the best way to support this channel. Any questions or comments, let me know down in the comments box. I'm loving the feedback and I'm loving hearing from you all. Other than that, thanks for watching. On the next video, on the next part, we are going to be configuring a spine leaf topology. Very different. Thanks for watching. Goodbye.